we have a special guest presenter, Professor Ken Collerson, who played a pivotal role in the discovery and characterisation of the North Stanmore heavy rare earth and scandium-enriched regolith deposit. At Victory Metals Australia, he is responsible for corporate technical leadership, and he is here to provide a technical talk on the geology of North Stanmore. Welcome, Ken.
Thank you very much, Michelle, for that warm welcome, and it's a pleasure on behalf of Victory Metals to present you some very exciting results that we've had in the last couple of years that really, I think, demonstrates Roy Woodall's view of exploration, that exploration discovery is seeing what other people see but thinking what no one has thought before. And I think what we've seen in the North Stanmore area is a good example of that. What I'll do is I'll take you through, I won't worry about that, but I'll take you through some aspects of what we're going to present this afternoon. I'll give you a bit of an overview of the discovery, so some take-home messages before you go to sleep. I'll then talk a little bit about rare earth systematics in Regolith and the way we represent rare earth data in a simple fashion that can be used and understood. I'll then talk about the source of the Regolith rare earth system that we've discovered near Kew. It's related to an alkaline intrusion which was previously undiscovered. I'll then run very briefly through some of the depth profile systems that we see in the regolith with respect to scandium and also the rare earth elements. I'll talk a bit about the mineralogy very briefly and show some SEM data for that. And then lastly, I'll talk about the leaching process that we're using and finally finish off with the reason that we have this deposit at North Stanmore in an arid area, which is a long way from the tropics and humid area where one normally associates these regolith clay type systems to form. The North Stanmore deposit is really quite large. The image on the right hand screen is an image showing the size of our exploration area. Imagine from Welch Pool to Cottesloe and south to Kwinana, that's the scale of the underlying system that we're dealing with. Our tenements are shown on the opposite screen, and we can see this is our area where we've developed the mineral resource estimate on 8% of the tenement area, of the exploration area. We've now done step-out drilling north and south, and we've proved the continuity of the underlying lithologies and also the continuity of the regolith rare earth system in that area. A bit of metrics concerning the deposit. It's a regolith-hosted, in some ways clay-bearing, but not all ionic clay system. It's near Kew, it's just north of Kew. We have an MRE of about 235 million tonnes, of which 149 million tonnes is indicated. It contains a substantial quantity of rare earth oxides, of which a substantial quantity is the heavy rare earths, which are the very high value rare earths. It's Australia's largest heavy rare earth dominated regolith discovery, and it has a heavy rare earth to total rare earth ratio of about 35% on average, but we're now seeing samples that are ranging up to 60 and 70%. It's a very, very dysprosium and terbium-rich system. It also contains copper, hafnium, nickel, cobalt, and also gold. So it's a system that is really very attractive. It has scale, grade, and value. The MRE is defined by two essential components. One component has a cutoff of about 330 parts per million, and that's shown in the brown ornamentation. But within that, we have in red a higher grade area. The brown ornamentation has an average rare earth content of about 532 parts per million. The red area about 1,000 parts per million. But the true value comes from the fact that this is heavy rare earth enriched. It's very substantially enriched in dysprosium and terbium, and therefore very different from the sort of some of the Brazilian rare earth systems that are receiving a lot of attention lately, Meteoric and Colossus. In terms of the behaviour of rare earths in regolith, the regolith deposits are the principal source of heavy rare earths, the principal source being southern China and Myanmar, although they don't like to talk about that very much. But the South Chinese deposits are developed over granites in areas of high tropical weathering. They're rather shallow, maybe 10 metres thick, and they produce the majority of the world's dysprosium and terbium. What we see in the system at North Stanmore is a substantially larger version of the Chinese deposits. The way it develops is that rare earths in the primary phase in the underlying intrusion break down monazite, xenotime, and I'll tell you how that happens through the presentation. And they're dissolved as carbonate or bicarbonate ions and migrate through the weathering profile where they concentrate at redox fronts. During that process, cerium 4+ is oxidized and migrates upwards in the profile. So the rare earth profiles that we're looking at for commercial activity are those that have negative cerium anomalies. They're the ones that have lost their cerium 4+. And we can recognize those chemically very easily. In fact, we can see them on this diagram here. I've plotted some chondrite normalized plots. The reason we do that, I'll explain that in a few minutes. But between lanthanum and praseodymium, in the top panel, you can see a spike upwards. That's a pattern with a positive cerium anomaly. Those samples have got cerium 4+ enrichment. They're enriched in the polyphylla rare earths. The samples that are best for the leaching characteristics are those with dips between lanthanum and praseodymium. Those are the samples with negative cerium anomalies, and those are the ones that we target in exploration. The reason we use chondrite normalized plots is to eliminate the Otto-Harkins effect, which is a characteristic of elements that even atomic number elements are present in higher abundance than the adjoining odd atomic number element. And if we just simply plotted concentration, we get a sawtooth pattern that we see on the screen here. When we divide those concentrations by the value in chondritic meteorites, and this was worked out by a Japanese geochemist, Matsuda, in the 1950s, we get smooth patterns. And here's a sample from North Stanmore. It's got about 4,500 parts per million total rare earths, very distinct negative cerium anomaly, a very characteristic niobium tantalum ratio, which is indicative of the plume source of these rocks, and that's what we call a negative cerium anomaly. The reason that this system is there is because of a plume track, and Marco Fiorentini postulated this in 2000 in a Nature Science report paper. He postulated a plume extending from Mount Weld through the northern Yilgarn towards Kew. This was before we discovered the North Stanmore intrusion. There are a number of alkaline systems along that, particularly in the Leonora area, and Etria near Leonora, and then there's a number of carbonatites that are also present along that trend. But North Stanmore, I think, is one of the big discoveries on that trend. Plume tracks develop when lithosphere migrates over a stationary plume in the mantle, coming from the core mantle boundary as a thermochemical upwelling, and they transport critical metals from their source in the mantle to the crust and lithosphere. Here's the system here shown in the magnetic feature, and we've extended our tenements to the south further. We've looked really only in this small area here. We've had drilled out north and south. The system consists of a very distinct bullseye here, which we've drilled at 250 metres in diamond core drilling to get samples of the ultramafic, mafic, intermediate, and felsic differentiates of the body. It's a bit like some of the intrusions on the Kola Peninsula in Russia, and this is a plot of a map of Kovidor intrusion. Highly complex and varied interactions of different lithologies, and this is what we believe is causing the variability that we see in the regolith above the North Stanmore intrusion. Here are some photomicrographs of some of the peridotites from the North Stanmore intrusion. They're chaosutite or amphiwol-bearing peridotites and carbonate-bearing peridotites and pyroxenites. In addition to that, we find gabbros, diorites, monzonites, cyanites, nepheline cyanites, and very occasionally alkali granites, and very minor carbonatite. The gabbros are undeformed, but beautifully preserved subophytic and ophitic textures. There are undeformed garnets, high titanium garnets in the system, which are very characteristic of alkaline systems. There's evidence of phenotization with blue amphibole developing around some of the primary ferromagnesian phases. To confirm that it's an alkaline system, a plot of thorium against cobalt is a good proxy. This was developed by Hastie and Julian Pearce. Thorium, a proxy for potassium, cobalt, a proxy for silica. You can see all of our samples plot in the alkaline field. The compositions define a beautiful igneous fractionation trend in terms of cobalt and nickel. The rare earth patterns in the underlying intrusion are shown in the bottom part of this diagram. The rare earth patterns in the enriched regolith are shown in red. You can see the range of lithologies are present: peridotite, pyroxenite, gabbro, high thorium gabbros, nepheline cyanites, and then the regolith developed above it. So the rare earth enrichment that we see is due to weathering and transport and concentration on redox fronts in the regolith. The underlying intrusion would be unlikely to be an ore body. There are carbonatites as well. This shows the rare earth patterns for carbonatites from a variety of Kola Peninsula intrusions, and the rare earth patterns for regolith samples that match that perfectly are shown in the ornamentation on that diagram. The niobium tantalum ratio is a key indicator of a plume system. Plume magmas have high niobium tantalum ratios, averaging about 15 to upwards of 3,000 in some cases. The continental crust has a niobium tantalum ratio of crustal rocks of about 10 to 12. So it's a very distinct discriminator. Also, when you look at the total data set we have from the niobium tantalum ratio, it's clear that we're dealing with an in situ regolith. It's not a transported regolith. When we look at the composition of the different rock types from our drilling, I've plotted on these two panels. They were from a paper by Lubert and Claude Alleg in 1972, but where he plotted lanthanum ytterbium ratio, which is essentially light to heavy rare earth ratio, against concentration of total rare earths. And we can see that all our samples, particularly those with cerium anomalies of 1, which match the sap rock and also the source intrusion, they plot right in the field of differentiated alkaline intrusions. In the weathering profile, where the cerium anomaly is less than 1, the samples shift to the right to higher concentrations, but they still occupy essentially the same source indicator on the diagram. This is what some of the regolith samples look like from one of our drill holes, plotting them on the diagram that has been recently publicised by Ota and Choi. And you see that our bottom of the hole samples plot in the field, in other words, the sap rock field, plotting very close to the unaltered source rock. But this diagram shows that we're dealing with a range of primary rock compositions, both felsic, mafic and ultramafic. Looking at the distribution of hyperspectral mineralogy of the system, we see the top of the system is characterised by kaolin, varying in thickness down to about 80 metres. It's locally a very, very thick weathering profile. Towards the bottom of the holes, we see Mg and Fe smectite appearing, and also we see montmorillonite and chlorite, particularly the Mg smectite reflecting the fact that the source is an ultramafic to mafic source. And this diagram shows quite clearly the sap rock composition. Down here, essentially, we're a cerium anomaly of 1. As in the enriched zone between about 35 and 40 metres, we see elevated heavy rare earth concentrations, and there we see a negative cerium anomaly. Above that, we have a positive cerium anomaly and somewhat lower concentrations. Just two panels that illustrate the relationship between cerium anomaly and depth, and depth and concentration of rare earths. You can see that the regolith in this area is very, very large. We see rare earth redistribution extending from essentially 10 metres to as deep as 80 metres. It's a massive system, very much thicker than anything coming from the South China granite regoliths. The systems that are attractive for us are obviously the ones that are in this field here with negative cerium anomalies, because these are enriched on this side. They're enriched in cerium 4+, which gives very little value to the total rare earth concentration. We see some very interesting patterns appearing when we look at depth profiles through the regolith. And these sorts of diagrams have not really been shown by other workers. We see concentrations occurring at different depths, for example, 12 metres, about 40 metres, and about 55 metres. But we see in some holes stacked concentrations with enrichments at a high level, then enrichments again at a deeper level. And this we interpret to reflect the fact that we're looking at variable water table depths. The water table being a redox front, and that being the zone where rare earths can precipitate. And here's some examples of our depth profiles that we see. We see rare earth enrichment occurring at between 15 and 25 metres, between 28 and 37 metres, between 41 and 46 metres, and also again between 53 and 77 metres. So very major changes in the water table in this very thick weathering profile. All of these, as you can see, are enriched in the rare earths with 1,000 times chondrites being very, very rare earth enriched. Scandium also is an element that is quite abundant in the system because of the pyroxenites that are present in the underlying intrusion. The limit down here on the bottom of the corner is 20 parts per million, so all of these are enriched relative to the crust. We have enrichments extending up to about 55, and in more recent data we've just received up to about 150 parts per million. So very interesting. Scandium normally associates with the transition metals, cobalt, nickel and copper, but we do see evidence in some instances that scandium is concentrating with goethite, and also some evidence that scandium is associated with some of the clays, which we can see here, and these are from a couple of holes. They are the same level that we're seeing the rare earth enrichment taking place. Some QuemScan data for the intrusion. We've done this at the JK Centre in Brisbane for samples with negative serum anomalies. This one a little bit, the bottom panel a little bit higher, this one lower, but we see that the rare earth bearing phases are present in very small fractions. We've actually beneficiated our samples by increased the grade by 100% by simply taking the minus 53 micron fraction. But with our process that we've developed through CORE in Brisbane, we're now looking at possibly being able to extract rare earths down to about 200 parts per million. One of the difficulties, particularly when you're dealing with xenotime-based systems, is explaining how xenotime can break down. Xenotime is a very resistant phase, and although monazite can break down in the weathering profile quite readily, xenotime is a little bit more difficult. There were two recent papers that appeared, one by Lee in 2022, where he speculated that biogenic activity, bacterial activity, may play a role in xenotime breakdown, and another one very recently by He in chemical geology, where he did experiments using a bacteria which released an organic acid, tartric acid, and that clearly showed that xenotime was being broken down with this organic acid. So what we believe is taking place is that microbes play a role in the weathering profile and developing of the regolith. Once the rare earths are released from their primary phases, they precipitate either as secondary monazite or as rhabdophane or churchite. And when they precipitate as at the water table levels. And so this explains what's going on, we believe, with respect to breakdown of the heavy rare earth phases in the underlying intrusion. We see this is an SEM image of some of the primary phases in the North Stanmore intrusion, some monazite and xenotime. We also have some monazite, some thorite and xenotime we have, and then we have secondary monazite developing in these fibrous phases. We can see the role of the more monazite rhabdophane compositions with this slightly fractionated rare earth pattern. The more churchite xenotime compositions have this elevated heavy rare earth concentration, but look, all have this negative serum anomaly. We've done a bit of work on recovery of rare earths. Before you can really produce a resource, you need to show that you can get the stuff out. This was our first attempts at CORE. In the blue ornamentation down here, the data from our first ammonium sulfate leaches, reasonably good recoveries of heavies, but not lights. We then approached it using magnesium sulfate adjusted with pH with sulfuric acid, and we can see we're getting between 80 and 100 and 90% recoveries across the rare earth spectrum. More recent work has shown we've improved it even further, and I can't divulge the licks of it at this stage because it's commercially confident. But you can see we've approached this from a very technical perspective and achieving very good results. And then finally, why it's there is an interesting story. And I always thought, regoliths develop in tropical weathering environments. Well, the time of weathering in this part of the world was between about 60 and 44 million years ago, which is the Eocene. Now, the Eocene corresponds to the Eocene thermal maximum. West Australia at that time was sitting down at high latitudes near Antarctica. This is the reconstructions of Cretaceous. But at that time, it's been predicted that tropical forests actually grew in Antarctica, and the Antarctic ice cap didn't form until 20 million years ago, contrary to some climate change people. And so what's happened is that at this time there were tropical forests growing where the North Stanmore intrusion had been intruded in the Proterozoic, and hence a very substantial amount of chemical weathering was taking place. In fact, it's been estimated that there was substantial chemical weathering occurring during this Eocene thermal maximum. So basically, the rare earths from the host minerals in the North Stanmore intrusion were broken down by biogenic activity, mobilised by groundwaters and precipitated in redox fronts at different water table depths. The rare earths were then concentrated in groundwaters, precipitated, and that's the different levels that we see in the very thick weathering profile at North Stanmore reflects these different water table depths. So basically, comparing to other deposits, this is a paper I've just sent off to All Geology Reviews in revision, showing some comparable regolith systems. In the big dots here are some of the Brazilian systems. China is down here, a tiny little dot, but a very large resource. If you look at the dysprosium, terbium to niobium, to niobium praseodymium ratio, that's when you see this very substantial increase in size of the bubble, and so that's why the Chinese deposits are so valuable, because of the amount of dysprosium and terbium. Over here, I've got our two estimates in North Stanmore. In the first one is our high-grade small deposit. The second one is the deposit of 149 million tonnes at 333 ppm cutoff, and then that's on 8% of the tenement of the exploration area. Extrapolate it to the full extent of the exploration area, we're looking at something about 2 billion tonnes of material. Just to finish off, Victory has discovered something pretty special in Western Australia. There's a long way to go yet. We've got the leaching experiments sorted. It clearly played a role in the chemical weathering during the Eocene, played a role in its formation. And so we're going to really say that global warming has provided a very good promoter of mineralisation. So thank you very much.